Good day, Dr. Sri Devi. My name is Ahmad, along with Ong Shi Nee and Lubna, are here to talk about the paper Multi-modal Transformer for Video Retrieval. Moving on to research problems, it is difficult to retrieve relevant contents to queries due to cross-modal cues. For example, of audience listening to a talk, if cues of audio and appearance are processed independently, neither of them can describe the scene unless they are processed together, which will produce a higher level semantics. Second is how to accurately extract related contents in long videos due to temporal information. Current approaches discard long-term temporal information in the video because of the long duration. An example of someone walking to me and someone walking away from me will have the same representation once moved temporarily, but the movement of the person is important in the query. Moving on to three research objectives is to develop a novel framework retrieval system using a multi-modal transformer architecture to produce actionable results based on 4 datasets by using the proposed framework and to determine different architectures for language embedding.
So forces are database are being used in the research, which are held to 100 million MRSR BTT, activity net captions, and LSMDC. These datasets consist of short and long YouTube videos ranging from 4 seconds to 30 seconds. The main idea of the methodology is that we will compute similarity between two elements, which are text and video. Then ranking is done according to the similarity, high value if I equals to j, and low value if I is not equals to j. The solution stage is divided into 4 parts. The first part is video representation. Self-attention layers allow the model to weight the importance of the words, while fully collected layers will further process the output of stack cell attention layer. The input is Ong. There are 4 elements in video embeddings. The first one is feature. First, we will attract video features using expert. For video V, each expert, which is a feature, attracts a sequence. Then all features will be projected into R power of V model. Aggregated embedding defines unit embeddings of each expert, and finally, the sequence of input features are defined. The second element is expert embedding E. It will process cross-modality information. And embeddings is learned to distinguish embeddings of each expert. Finally, the sequence of expert embeddings is defined. Next, moving on to temporal embeddings. It provides temporal information about time in video. TAGG and TUNK are used to aggregate features and unknown temporal information features. Finally, the sequence of temporal embeddings is defined. The last one is multi-modal transformer. It will show the input in Ong and produce video representation of psi AGGB. It's important to note that only aggregated embedding per expert are kept. Next, we'll move on to caption representation, which is divided into 2 stages. First, we will obtain an embeddings HC of the caption and then project it into function G into n different spaces. Next, we'll move on to similarity estimation, and it will focus on finding the video caption similarity based on the formula. Lastly, we'll go to training. The bidirectional max margin ranking loss is used for the training, and is often used in deep learning models for learning a joint embedding space for 2 modalities. The loss enforces embeddings that produce higher similarity scores for true pairs compared to negative pairs.
Our first finding in this paper is the impact of removing stop words in captions, and the results are shown in the figure. Removing the stop word helps generalize by bridging the domain gap between datasets. In this case, it is how 200 million and MSR BTT. However, when fine-tuning is done, it is better to keep all the words as they contribute to the semantics of the caption. The second finding is the comparison of the different experts. There were 3 experiments. The graph at left used only 1 expert, the middle used all experts, while the right one gradually add expert by greedy search. For using only 1 expert, the most shared expert provides the best result with the lowest mean. OCR has the poorest performance as speech and face are absent from many videos. The audio expert alone does not provide good result, but it contributes the most when used with other expert due to its complementary cues. In conclusion, MMT is an effective approach which can jointly learn from visual and textual inputs and outperform previous methods that use either modality alone. It also achieves state-of-the-art performance and lastly can effectively leverage both temporal and cross-modal cues, which are crucial for accurate video representation. That's all from us. Thank you.